Good morning, AOBI. This is Mr. Dunning. Stand by. I have a math lesson for you. Last week, all week, we looked at circles and pieces inside them and sometimes outside, secants and chords, tangents. Well, this week, today and tomorrow, we're going to be looking at circles again, but in a different way. We're going to be looking at arc lengths, not the length of straight lines. Now, we're going to need a little bit of information in order to do that. So stand by. I'm going to show you how to do it. It's easy, and I know that you can get a little bit of a review before we get going. We learned that there are 360-degree angles around a point. That half of those, or 180 degrees, lies on one side of a line through that point. We also learned that if we put that point in as the center of a circle, like this, it makes sense that the circle also has 180 degrees. Today's job is twofold. First, we're going to look at how much of the 360 degrees that angle accounts for. That's job number one, angles. Job number two is a little different. We're going to look at how much of the circle that red arc is. Now, it would help if we knew at this point how big the whole circle was. So stand by. We're going to learn both of those things today. We're going to begin our discussion by looking at a radius. Now here's where the discussion gets a little bit new. What we're going to do is we're going to lay radiuses along the circle, end to end, it turns out that we can get six, a little bit more than six radiuses. In fact, it turns out to be a little bit more than 6.28 radiuses. That's 2 pi. So the distance around a circle, the circumference of the circle, is going to be 2 pi times the radius, because there are 2 pi radiuses to get us all the way around the circle. So this length here The circumference, this length, is the distance around the circle in terms of the radius. If we know the radius, or the diameter, which is 2 radiuses, we can compute the circumference. Bear in mind that the circumference is a length. It's not an angle. Over here on the angle side, angles. So they're 2 pi of what? Good question. 2 pi of what? Well, the angle subtended by an arc of 1 radius, this angle, is called a radian. The angle subtended by 1 radius is 1 radian. So there's 2 pi what? Radians in a circle. So 2 pi radians is exactly the same measurement as 360 degrees. It's going to help our cause to switch back and forth quickly and easily between radians and degrees. It's really easy. In example 1, we're going to tell you that 360 degrees, all the way around the circle, angles all the way around, is the same as 2 pi radians. Now, we need for you to use a little common sense. Half the circle, the way you're used to seeing it, is 180 degrees. But half the circle in radians is pi. Pi radians. Half of this is 90. And that would be pi halves. Pi halves radians, 90 degrees. Half of that over here would be 45 degrees. And over here, pi fourths radians. The conversion back and forth is really not that hard, especially when they give you nice angles. Okay? Let's look at another nice angle, 60. It takes 3 of these to make pi, or half the circle, radians. So each one of them is going to be pi thirds radians. We'll use radians to solve a couple of these problems coming up. And we're going to be going back and forth between degrees and radians because sometimes it's easier to use radians. In example 2, we've depicted a central angle of 90 degrees. 90 is obviously easy to write in degrees, but it's equally easy to write in radians. Pi halves radians is exactly the same measure as 90 degrees. Because this is pi radians, half of it is 90 degrees, or pi halves radians. And about this time, you're wondering, why all the fuss? Well, sometimes working with small numbers can be a big help, and radians can help us do that. Now, clearly, if the angle is 90, angle here is 90, you can see that this piece of arc is going to be 1/4 of the circle. Clear? Sure. So, the arc is going to be 1/4 of 2 pi r. Remember, 2 pi times the radius is a length. It's the length of the circumference, and we want 1/4 of it. Okay? When we do the multiplication, we get 1/2 of pi times the radius, or pi halves times the radius. But, wait a minute. Wait, make the connection. Come on, make the connection here. This angle in radians is pi halves. See, I told you it would be easy. Look at the same calculation here. We're going to compare pi halves (90 degrees) to the whole circle. This is the 90-degree piece. This is the whole circle, 2 pi radians. The answer? This piece is 1/4 of that piece. Exactly what it shows over here. I'm going to give you a moment to digest that before I put up one more example. In example 3, we're going to make a comparison between an angle in degrees and the whole circle and the piece of the arc to the whole circle. Let's do a picture. Our angle in degrees is 60. In radians, that same angle is pi thirds radians. How much of the total 360 is this? Well, 60 divided by 360. Notice that you're working with big numbers here, much bigger than you will here. Watch. You'll see it. Working with radians, if we have this angle of pi thirds compared to the 2 pi radians, it would look like this in algebra. Pi thirds over 2 pi. That gives us 1/6 without the big numbers. Working in radians can be a big help to you. One more example to help you get the cross here between degrees and radians. In example 4, I've depicted an angle of 45 degrees. 45 degrees is half of 90. So it would be pi fourths radians. Same angle. We can call it 45 degrees. Or we can call it pi fourths radians. When I compare this to 360, the arithmetic is a little bit more difficult to watch. When I compare pi fourths to 2 pi, compare pi fourths to 2 pi, the answer is quick and easy. This arc is 1/8 of the circle. Working with radians can sometimes be much faster, and it will always give you smaller numbers. So I'm encouraging you to learn what a radian is and how to work with them. Our next step in this is to look at how long is the circumference. Because remember at the outset, what we said is we were going to find out how long a piece of arc is. Well, we can't use all of the stuff we did over here until we know how long the whole circumference is. So let's do a couple of specific examples. In this example, for the first time, now we have a radius. And that means we can compute how long the distance is around the circle. Let's do that. It will be 2 pi times 10, or 20 pi. 20 pi is a distance. That's the distance around the circle, radius 10. Now the question before you is, how much of that is taken up by this piece of arc? So let's do our calculation over here. In degrees, we have 30. In radians, pi 6. So we want to compare 30 to 360, and we want to compare pi 6 to 2 pi. Here we get 1/12. Here 1/12. Notice in the angle, when you do this calculation, the pi disappears. it reduces to 1. It cancels, goes away, leaving just a fraction. So this piece here is 1/12 of the whole circle. In order to calculate that, algebraically, what we're doing is saying we want 1/12 of 20 pi. This is 1/12 of the circle. This is the circumference of the circle, 20 pi. We want 1/12 of 20 pi. Well, we can do a little bit of simplifying here. That's going to be 5/3 times pi. That's how long this little piece is. About this point, you're saying, well, do I need to put no? Leave it just like that. I've told all my students, and I'm telling all of you now, leave pi alone. Don't try to use 3.14 or some number like that, 22/7, forget it. Leave pi as pi. This answer is exact. If you put in a number for pi, the answer is approximate. I hope you all had a very happy Easter, and I hope the Easter Bunny just brought you tons of covered eggs. You can crack them open, make egg salad, and all kinds of good stuff. Happy belated Easter. We'll see you tomorrow.